Artificial intelligence feels almost weightless. You type a question, an answer appears. Generate an image, and seconds later, it exists. Build software, analyze a document. Create a video. To the person using it, AI seems to live somewhere inside the internet, but it doesn't. Every prompt, every generated image, every AI model eventually leads to a physical machine. And those machines need electricity, a lot of it. Behind the AI boom, America is building enormous data centers, filled with thousands of powerful computers, running day and night. And now, something unexpected is happening. The technology is advancing faster than the infrastructure needed to power it. America spent decades building the digital world, but the next stage of that world may depend on something much older: power plants, transformers, transmission lines, and an electrical grid that was never designed for the speed of the AI revolution. This is no longer just a technology story. It is becoming an energy story, because the biggest question facing America's AI boom may soon be surprisingly simple. Where will all the electricity come from? When most people imagine artificial intelligence, they imagine software. But AI begins with hardware. Inside modern data centers, rows of servers stretch across enormous rooms. Thousands of processors perform calculations simultaneously. Some train AI models, others run them millions of times for users around the world. And these machines don't just need electricity to compute, they generate heat, which means they also need enormous cooling systems, pumps, fans, networking equipment, backup systems, power conversion equipment, all operating continuously. According to the International Energy Agency, servers account for roughly 60% of electricity demand inside a modern data center, and AI is making those servers more powerful. Traditional internet infrastructure was already large, but AI requires something different: accelerated computing. Massive clusters of specialized processors working together. The result is a new generation of data centers that can require extraordinary amounts of power. Some new facilities are being designed at the scale of hundreds of megawatts. Others are approaching 1 gigawatt. That is no longer just a building. It is an industrial-scale electricity consumer. For years, America's electricity system had something close to a luxury. Demand wasn't growing very quickly. Between 2005 and 2019, U.S. electricity demand increased by only around 0.1% per year. Utilities could plan around a relatively stable future. Then, the pattern changed. Between 2020 and 2025, electricity demand grew by roughly 1.7% annually.
And one major reason is data centers. In 2018, American data centers consumed roughly 1.9% of the country's electricity.
By 2023, that had risen to approximately 4.4%, and according to estimates produced by Lawrence Berkeley National Laboratory, by 2028, data centers could consume somewhere between 6.7 and 12% of all electricity used in the United States. Think about that. At the upper end, roughly 1 out of every 8 units of electricity consumed in America could be going to data centers. And the International Energy Agency sees the pressure continuing. By 2030, American data center electricity consumption could increase by roughly 240 terawatt hours. Compared with 2024, the AI revolution is becoming visible on the electrical grid. But there is an important distinction. America is not simply running out of electricity. The real problem is more complicated. Electricity has to be generated at the right time and delivered to the right place. And data centers are not distributed evenly across the country. They concentrate Virginia, Texas, Ohio, Pennsylvania, and other major computing hubs. This matters because the grid is regional. A power plant hundreds of miles away cannot automatically solve a local bottleneck. Electricity must travel through transmission infrastructure. Substations must handle the load. Transformers must convert the power. New generating capacity must connect to the system. And all of this takes time. The International Energy Agency describes a growing scramble, not only for electricity, but for grid connections. And that creates a strange mismatch. A technology company can move extraordinarily fast. Capital can be raised, AI chips can be ordered, a data center project can be planned, but the electrical infrastructure supporting it may operate on a completely different timeline. The digital economy is colliding with the speed of physical construction. Nowhere is this challenge clearer than the region managed by PJM, America's largest electricity market. PJM coordinates electricity across 13 states and Washington, D.C. It includes Northern Virginia, home to one of the largest concentrations of data centers on Earth, and PJM is preparing for enormous growth. Its projections show summer peak electricity demand increasing by roughly 70 gigawatts over the next 15 years. But something even more striking appears in its shorter-term forecasts. Between 2025 and 2030, data center growth alone could add up to roughly 30 gigawatts of electricity demand. 30 gigawatts. That is not a small adjustment. It represents an entirely new category of load, appearing within just a few years. And regulators have noticed. The Federal Energy Regulatory Commission has already been examining how massive AI data centers should connect to generating facilities, while protecting grid reliability and preventing unfair costs from being pushed onto ordinary consumers. This is where the AI story stops being just a Silicon Valley story, because someone has to build the infrastructure, and someone has to pay for it. Technology companies understand the problem, and their response reveals how serious the energy question has become. Microsoft signed a 20-year agreement connected to restarting 3 Mile Island Unit 1 in Pennsylvania, now planned as the Crane Clean Energy Center. The project is expected to return approximately 835 megawatts of nuclear capacity to the grid. Meta has gone even further. Its nuclear agreements involving several American energy companies could support up to 6.6 gigawatts of new and existing nuclear capacity by 2035. Tech companies are also pursuing solar, wind, geothermal, natural gas, battery storage, and next-generation nuclear reactors. This would have sounded strange. During the earlier internet era, the world's largest technology companies are increasingly becoming major players in America's energy future. Because owning the best AI model means little if you cannot secure the electricity required to run it. But there is another complication. Building clean electricity infrastructure takes time. AI demand is arriving now, and according to the International Energy Agency, renewables are expected to supply a major share of new data center electricity demand, but not all of it. Natural gas, and even coal in some regions, are expected to help fill part of the gap in the near term. That creates a paradox. AI is often presented as the technology that could make industries more efficient, optimize transportation, improve scientific research, manage electrical grids, accelerate clean energy innovation. Yet building the infrastructure needed to power AI could also increase fossil fuel electricity generation, at least during the transition. The technology that may help redesign the energy system first needs enormous amounts of energy from the system that already exists. There is another reason this moment matters. America has experienced major electricity demand growth before. Factories expanded, air conditioning spread, millions of homes added appliances. But AI infrastructure behaves differently. A giant data center can appear as a massive block of demand in one specific location. It needs reliable electricity 24 hours a day, and companies building these facilities are competing globally. America is not only asking, can we power AI? It is asking, can we power it fast enough? Because China is building AI infrastructure too. Other countries are expanding computing capacity, and electricity availability could become part of technological competitiveness. For decades, the strategic resources of the digital economy were chips, software, talent, data. Now another resource is joining that list, megawatts. And this changes how we should think about the AI race. The next major AI breakthrough may happen inside a laboratory, but deploying it at enormous scale requires infrastructure outside that laboratory. Power generation, transmission, transformers, cooling, land, water, construction, permits, supply chains. The intelligence may be artificial, but the infrastructure supporting it is extremely physical. And that may become one of the defining contradictions of the AI age. Software can scale almost instantly. Electricity systems cannot. You can copy software in seconds. You cannot copy a power plant. You can deploy an AI model around the world overnight. You cannot build thousands of miles of transmission lines overnight. AI moves at digital speed. The power grid moves at industrial speed. So perhaps there are actually two AI races happening in America. The first is the race everyone can see. Who builds the smartest model? Who develops the best chips? Who creates the most powerful AI? But beneath it, another race has quietly begun. Who can build the data centers? Who can connect them to the grid? Who can secure enough electricity? And who can do it without making power less reliable or dramatically more expensive? For everyone else, the winners of the AI revolution may not be decided only by algorithms. They may also be decided by power plants, transmission lines, and something humanity mastered more than a century ago: electricity. Because the future may run on artificial intelligence, but artificial intelligence still has to plug into the wall.